Hello and welcome to Gen Chem 2 laboratory exercise LeChatlier's principle. Now, LeChatlier's principle is the major scientific contribution of the French scientist Henri-Louis LeChatelier, named after him because of his work on it. What he has taught us is that due to inefficiencies in reactions and due to a phenomenon called equilibrium, reactions never produce the maximum yield that you expect. So when we write a chemical equation, this equation demonstrates the maximum possibility. It assumes that everything works perfectly and that all of the reactants are converted entirely into products. But we learn from LeChatlier's work and from observation in our own lives that eventually there reaches a place where no longer is there any change, no longer is there any progress, and the reaction circumstances reach a state where the reactants cease to be continually converted into products, and where the products have a reverse reaction in some cases and revert from products back to reactants. This is the basis of the biological phenomenon known as homeostasis, wherein the chemical processes that are essential to and govern the behavior of all living systems are maintained in some sort of a balance, where there is a relationship of equilibrium between the reactants and the products for the maximum benefit of the organism or the system, if this is a purely chemical example. So in any system, based on the circumstances, there is a place at which, even if we start with an excess of reactants, the reactants cease to continue to create an increase in the deposition of product, known as dynamic equilibrium, where even though the reactants continue to collide and create products, also the products collide and reverse reactants, and so we reach a place where there is no net change. There is still change occurring, but there is no net change in the system. All reactions, no matter how well you set them up, never produce the maximum amount. This is why in Gen Chem 1 we talked about theoretical yield and actual yield, because we are concerned with and interested in the degree to which we are able to convert reactants into products. But it is never a completely efficient process. Also, we learned from Mr. Miyagi, the Pat Morita one, not the Will Smith one, all life have balance. And this is the chemical representation of the reactions that occur in a living system that create a balance and allow things to persist as they are. So LeChatelier spent some of his life's work describing this. The irony is that we are going to, in the lab manual, use what is known as the Haber process to demonstrate the principles that LeChatelier defined. And the reason why this is slightly ironic is because this is one of the reactions on which LeChatelier was working when his lab exploded. This is known as the Haber process. And if he had discovered it, it would be called the LeChatelier process. But he referred to the inability to come up with this first as one of the great failures of his life. But it is still an important illustration because it illustrates all of the facets that can change in a reaction and allows us to talk about them in their net with all the possible outcomes. So LeChatelier's principle can be summarized as following. If a chemical system at equilibrium, which is what this arrow here demonstrates, experiences a change in temperature, pressure, or concentration of any of the components, the equilibrium will shift in order to minimize the change to the system. Okay, so you can think of it as a teeter-totter, where if it is perfectly balanced, if you put pressure on one end, something will happen to the other end in order to restore it to its equilibrium. Or otherwise stated, for every action, there is an equal and opposite reaction that restores the system to a balanced state. So in the Haber process, we see all of the three possibilities for changing the balance of a system. talk about these individually. For temperature, there is a temperature component indicated here as one of the products of the reaction. So changes in temperature can affect the balance of the reaction. If you raise the temperature, that is adding energy to the system. So adding energy to the system is the same as pushing on this end of the lever, and so something will happen at the other end to restore balance. If the temperature were on this side, it would be the reverse, where if it was an endothermic reaction and energy was consumed, then adding energy by raising the temperature would cause the reaction to move towards the products to compensate for the increased change on the reactant side. So temperature is a measurement of energy. So if you know the energetic exchange of a reaction, then you can predict the behavior. So if I raise the temperature of this, because it is exothermic, it will shift towards the reactant side because I have added extra energy here, which is the same as increasing this. We're putting pressure on the product side, causing a shift back to the reactants, as indicated by this arrow. If I were to lower the temperature, that would be the same as removing this. That would be relaxing the pressure on this side, on the reactants or the product side. If you remove the temperature, lower the temperature, causing it to drop, therefore something here would have to change as well on the reactant side. And so it would shift to the right to compensate because you're removing the energy. Okay? Pressure is a phenomenon that affects reactions only in the case where gaseous reagents are present. And the Haber process includes only gases. So we have nitrogen gas, hydrogen gas, and ammonia gas. Okay? And pressure is inversely related to the number of moles of gas present. Okay? So the reactant side of this has 4 moles of gas, and the product side has 2 moles. There are 3 moles of hydrogen gas and 1 mole of nitrogen gas on the reactant side, and there are 2 moles of ammonia on the product side. So increase in pressure favors lower number of moles. Okay? And that's because anytime you put pressure on a system, you're forcing the molecules together, and so the tightly you pack it, it's more favored. You can think of it as getting into an elevator. That's a contained system, and which is more comfortable for you when there are fewer individuals in a contained, defined environment, or when it is chock full. And chemicals behave the same way in that particular instance. Lower pressure favors allows for an increased number of moles of gas. So you're only considering the gases. This one only has gases, so we'll think about that. So if I lower the pressure, then it will shift towards the reactant side because it will allow for the evolution of more moles of gas. If I raise the pressure, it will favor the product side because there are only 2 moles of gas. And of course, this is doing them one at a time. And then we can change the concentration. And changing the concentration of any component has the opposite effect. Okay? So if I remove a reactant, then I have to remove a product. If I add a reactant, then I generate more product. If I remove the product, I have to remove more reactants, which causes a shift. And if I somehow, for some reason, would add more product, then it would shift back to the reactant side of the equation. So what we're going to do in this laboratory exercise is we're going to modify the circumstances of several reactions and then observe the changes, if any occur, and then describe what happens according to LeChatlier's principles. And it's important to note the difference between an observation versus an explanation. Okay? An observation is simply what you see. It is not a description of what happened. Okay? An explanation is the rationale and the reasoning why you observed what you saw. Okay? So we have chosen for you in this laboratory exercise a series of examples where one of 2 things will occur. We will either have a precipitate that will either form or disappear. That is your observation. that the precipitate either increases or the precipitate disappears, or they will be colored solutions. Okay? So a change in color is the observation, and the reason why the color changed is your explanation. Okay? So for each of the reactions that we're going to be looking at, we want you to note what you observed, and then tell me, according to LeChatlier's principles, why that change occurred in the system. Okay? Most of the reactions that we'll be looking at will be changes in the concentration one way or another. For many of them, we will be directly changing the concentration, and that is because those are substances that we'll be adding that have one or more of the components. Okay? So if I had a reaction that included a sulfate ion, okay, then I could add magnesium sulfate, or that's not very soluble, so we'll use sodium sulfate, and that would be the same as introducing sulfate into the balance, okay, because we're adding a component. The other kind we are using is consequential change to the concentration. Okay, that's a delta for change. Okay, consequential change to the concentration. That is in the case of reactions that deposit or produce either hydroxide ions or hydrogen ions that are either acidic or basic, and so we're going to add a substance that will remove this. So in order to remove a base, I will add an acid of some sort, and that will consume this and remove it. If I want to remove an acid, then I would add a base. These are just examples, because the base will remove this from solution and then cause a resultant shift. Okay? There is one for temperature, and owing to the circumstances required in order to change the pressure, this is a principle that we want you to understand. So I'll just go over them one more time. Changes in temperature are treated as if the energy is involved directly in the reaction, as with the Haber process. In the Haber process, the energy is a product of the reaction, and so changing the temperature is treated the same way as changing the concentration of the energy in the solution. Pressure affects the number of moles of gases, and the pressure change is inversely related to the number of gases. Ergo, if I raise the pressure, I like less gas. If I lower the pressure, I like more moles of gas. And then any concentration is simply equivalent to changing the actual pressure on one end of the teeter-totter or the other. If I remove something from one end, I must remove something from the other. If I add something to one end, I will result in an add to the other in order to restore the balance. Okay? So if I add something, I must add something here to restore the balance. If I remove something, I must also remove something from the other side and return it to balance. And no equation is perfectly balanced. We generally represent this, but we'll discuss partial equilibrium in a later laboratory of this course. Good luck with your exercises. Thank you for your attention, and have a great day.
All right, today we're ready to do part A of the LeChatlier's principle. We first have to set up an equilibrium of sodium chloride with water. This is the first equilibrium that's written for you. We just need a scoop of sodium chloride, and then we have to create a saturated solution. The best way to create a saturated solution is add just enough water to cover it and then shake vigorously for at least 60 seconds and see how much of it dissolves. And if it all dissolves, then we need to add more sodium chloride. But if after 60 seconds of shaking we still have solid crystals at the bottom, and it looks like we still do, we can proceed to the next stage. So we're going to shake and check, still see crystals. We'll shake and check one more time. And as you can see, there's still crystals on the bottom. What we need is the supernatant. If we've done this correctly, we have saturated the water. It can no longer hold any more crystals, so we're going to decant the liquid now into a second test tube. We'll put the first test tube in there, and we now have a saturated solution of sodium chloride. We have set up our equilibrium. We are now going to stress the equilibrium by using some concentrated hydrochloric acid. I'm going to switch test tubes for a moment and set this up so we can try to see what happens directly in the test tube. So it should require only 2 or 3 drops. So we added a drop, we add another drop, and we should notice something happening inside of our test tube. And if we look carefully, we'll see that the test tube has now filled up with crystals on the bottom. Let's see if we can show that in a clearer method. All right. There we go. The light. All right, and that's the end of this experiment part. Okay. Okay, for part B of the LeChatlier's lab, we have a pre-made equilibrium of potassium chromate. We're going to add a small amount of, pause it, let's start over. I'm missing 2 chemicals.
Okay, just keep going and we'll trim it.
Okay, we're going to first stress it. Just have my sodium hydroxide, take too long. I'm supposed to do it. Okay, blooper reel. Okay, we're going to first stress the equilibrium with some nitric acid. And as we added just 3 drops of nitric acid, you should have noticed a nice color change, and we are no longer a yellow color, but we have changed to this orange color. Okay, that was due to adding nitric acid and stressing equilibrium. We are now going to add some sodium hydroxide and see if we can return the equilibrium to its previous position. And if you watch carefully, took about 4 drops, 5 drops in total, and we are back to our original equilibrium position. And that concludes your observations for part B. Very fast. Okay.
It's nice to follow up the order and clock with what's out in there.
The pause button.
Alright, for part C of LeChatlier's principle, we're going to do a series of equilibriums using silver as our common ion. We're going to first start by adding 2 squirts. Well, that was a big squirt. We'll just do 1 large squirt of silver into our test tube. Our test tube looks like it was slightly contaminated, but it won't affect LeChatlier's much. There's that haze, should not be there. Let's try a second test tube. See if it comes out clear. Okay, much better. So silver will show you any contamination in any of your glassware almost immediately. So we have our silver nitrate. We're going to now add an equal amount of sodium carbonate and set up our first equilibrium. And if you remember your solubility rules, carbonates precipitate with nearly everything. and we should see a lovely white solid forming as we added the carbonate. Okay, and I'm going to add a little bit of excess carbonate because we are going to try to keep the solid and decant off the supernatant. This will take a few minutes for the solid to precipitate mostly to the bottom. I don't know if you can see the bottom very well, but it's a lot thicker white than the top is. As we let it settle, we are now ready for decanting. We're going to decant this top liquid into a waste beaker, and as much of the liquid off as possible, and then we want to just save the solid. Okay. Alright, we now have some solid sodium carbonate, and just like with the sodium chloride earlier, it's in equilibrium with the solution, so technically speaking we've created a saturated silver carbonate solution. Sorry, that is silver carbonate solid. We're now going to stress that equilibrium by adding some nitric acid, and we're going to do this dropwise. The key is to minimize the amount you use here. Try to do it as few drops as possible, and we did it in just 2 drops, and we should see that our solid is now turned perfectly clear. Okay, so you are to report how did the nitric acid affect the previous shift. And now we're going to set up a new equilibrium by using hydrochloric acid. We're going to add a squirt of this, and again we see a lovely solid, milky, creamy white precipitate forming. We'll keep this here. We're going to let this one settle just like we did the first one, because most of the silver is going to be into the solid, and you'll see that it's really thick at the bottom, it's kind of lighter on top. After we let that settle, we're going to do the same thing. Try to decant off the supernatant and keep the solid as much as possible. Solid's floating. Alright, we are going to make do with that. A lot of our solid is floating on the top. Our next equilibrium shift is with ammonia. We have concentrated ammonia here, also known as ammonium hydroxide. Ammonia has the ability to create complex ion formations with many metals, especially in the transition metals. And we're going to try to shift the silver chloride equilibrium by stressing it with a concentrated ammonia. Now, if this works, this is the equilibrium that's actually missing from your procedures. And we still have a few solids at the bottom. Shake them gently until all the solids disappear. This equilibrium of forming a complex ion requires 1 silver complex with 2 ammonia molecules to create a it's called a diamino silver 1 complex. And we're going to shake it just gently here until all of the solid has dissolved. And if it doesn't, we're going to add 1 more drop of ammonia. Maybe 2. Okay, our solid has completely dissolved before, so the silver chloride equilibrium has been shifted by the concentrated ammonia. And now we set up a new equilibrium between ammonia and silver. Again, it's 1 silver and 2 ammonias to make the complex ion. Our last shift of this equilibrium will be to use some sodium sulfide. And so sodium sulfide is going to interact with the equilibrium that we currently have sitting in the test tube. And again, we're just going to add a squirt and look for change. And there we go. We have the lovely color of silver sulfide. This, as people would recognize, is the tarnish that occurs on silver items in your house. It's also used to help make glasses that change color in the sun by shifting equilibrium. And that concludes part C of this experiment. Okay, gotta make sure I have droppers.
At least you had a helper.
Yeah. I was going, where's the dropper? See, that. Okay, for part D of the experiment, we're going to do equilibriums with copper. And it's going to have an equilibrium between a copper bromide complex versus a copper water complex. And the equilibrium is already written in your lab manual, so please copy it down exactly. To set up the equilibrium, we're going to first take this copper bromide. You notice it looks kind of black or dark brown. And today, there's only 2 colors that we're going to care about, and that's green or blue. So even if it's dark brown, we're going to say it's actually dark green today. I know it's not exactly true, but it'll be true enough. The first equilibrium we're supposed to set up is by adding 20 drops or 1 milliliter to our scoop of the copper 2 bromide. Now it is extremely dark green here. Let's try showing it with a white behind the background. And it's so dark green and it's turning reddish brown. We are going to call this dark green, even though it looks reddish brown. This is our initial equilibrium. We have a high amount of copper 2 bromide complex that gives us the greener color. We're now going to stress it by adding 9 more milliliters of water, and we're to ask the question, does it turn greener or does it turn bluer? And you can also say, does it go more blue or does it go more green? That means the same thing. So, as we add the water, you'll see, is it turning bluer or is it turning greener? I need to do a fast shake. And we're almost added the 10 milliliters. You see, as we add water, does it turn bluer or does it turn greener? Alright. So, what did the water do to our shift? Did it shift it to the bluer side or to the greener side? Alright. Now that we created this equilibrium, we're actually going to divide it into 3 parts. We're going to keep one part as a reference. So it doesn't have to be exact. We just want to do approximately 1/3 of each liquid in 3 test tubes. Alright, so we should now have 3 test tubes with about the same aquamarine color in each. One of the test tubes, we're going to take and immediately stick it in an ice bath. And we're going to ask the question, and back here is our ice bath, so we're going to move the ice bath right there. And we're going to ask the question, does it go bluer or greener? This One we're going to keep as a reference, then the third one we're going to first add about the size of a grain of rice, a tiny amount of potassium bromide straight into the equilibrium, and we got to ask ourselves, we're going to look closely at the bottom, is it going greener or is it going bluer? Okay, write down in your notebook, does it seem to go greener? And just a reminder, any shade of brown is considered greener. Not that I said that. Okay, now we're going to take this one and we're going to stick it into a hot bath, which we have back here. We'll try to bring it forward and put it on the side. And we're going to let it sit now for about 5 minutes in each. It usually only takes about a minute, but we need it to go long enough to be able to answer the questions. Does it go greener or does it go bluer when we add energy, or do we take away energy? So let's look now at the one that was in the ice bath. Again, I'm going to put a white towel up here. This one in the middle is our reference. This one was in the ice bath. The one that's on your right. Did it go bluer or did it go greener? Should we see it? And if in doubt, we can put it back in a little longer. Now, we'll do the same thing with the one that's in the hot bath. Did it go bluer or did it go greener? You should not have the same answer for both. So back to the ice bath. Did it go bluer or did it go greener? Now, what's really fun with this experiment is you can switch places. Put the one in the hot bath into the ice bath, and the one in the ice bath put into the hot bath, and give them about 5 minutes and see if they will shift like they did before. So that's what we're going to do right now. Let's just give them a couple minutes to see if they shift. Actually, it looks like they're shifting in about 30 seconds. This is really nice. Okay. Ice bath, hot water bath. Let's look at the hot water bath first. Did it go greener or did it go bluer? And now we'll look at what happened in the ice bath. Did it go greener or bluer? And you should see the same effect. Thus, you should be able to determine whether this equilibrium is endothermic or exothermic. And that concludes Part D of LeChatlier's principle.